This is the start, as it says, of Lecture 9. This is the third lecture on Chapter 22 regarding the respiratory system. If you've ever had a chance to go into a cave, and I'd love to see how many of you, with your hands raised, have been into a cave. If you haven't been in one, you can imagine that caves start out typically pretty wide open. We tend to enter in the biggest regions. But as you explore further and further into the cave, you reach narrower parts, and there are even side branches that if you peer into them, and maybe travel into them, crawl into them, squeezing into these spaces, you see that the cave has smaller and smaller extensions. That's exactly where we're at now in our exploration of the movement of air into the lungs. We've made our way already in the system into smaller and smaller tubes. We're now going to explore the terminus, the end, the functional part, the alveoli, where the gas exchange really occurs. So here's figure 2212 in the Saladin textbook. And what you can see is that there's a really puffed out region that's full of all sorts of different kinds of cells that we're going to explore. Bronchioles, and here's one bronchiole here. Bronchioles, this one, is the result of already a lot of branches that we've been following. So if you imagine an oak tree somewhere on campus, there might be an oak tree, got a big trunk, and then coming off that trunk are some other major branches. Who knows, maybe 10 if it's a big tree. And then off each of those big branches are smaller and smaller branches, and that's what we've been following. And now we've made our way to what's formally called a bronchiole. These are 1 millimeter or less in diameter, and what's really significant here is that we've reached now the point where there's no longer the infrastructure. There's no longer the internal support of cartilage. We're reaching a very flexible, elastic portion of the respiratory tract. A pulmonary lobule, as is labeled here, and that's largely what we're looking at in this picture then, is, as it says, the part of the lung ventilated by one bronchiole. Has a cuboidal epithelium, and we said already that the height of the epithelium is growing smaller and smaller into the deeper recesses of the lungs. There's also a well-developed smooth muscle layer here, and so let's give some thought to that. What on earth is that smooth muscle doing here in this deepest areas of the lungs? Well, it's this smooth muscle that's regulating the diameter of the bronchiole, and then, as you can see, leading into the terminal bronchiole. That can close up a little bit and reduce blood flow into one part of the lungs. It also can overreact and lead to problems like asthma. Okay? It's these smooth muscles in the deepest areas of the lungs that form some of the biggest problems for people who have too narrow passageways. The only way I can really try to help you understand this for those of us that don't have this problem is imagine trying to drink through a very small straw. You can't move much through. You can try all you want to suck a little harder, but you can't move much through. And we'll return to asthma and talk about it a little bit later. So a bronchiole is going to divide up into, as you can see, we're just looking at one or two of them here, terminal bronchioles. So a bronchiole divides into terminal bronchioles. And these are the final branches, as you can see, into the respiratory system. Terminal bronchioles are about half the diameter. And interestingly, they don't have any of the mucus glands or goblet cells. They have cilia instead that are functioning to move back any of the mucus that's drained into this part of the lungs. And we're going to talk about the problem of the alveolar sacs filling up with fluid And the answer is going to be it makes the alveoli very inefficient for gas exchange. So what we've got are mucus production that's farther up the lungs. And now, once we're into the terminal bronchial, we're not producing any more of that mucus. In fact, we're trying to sweep it upward by that mucociliary, okay, let's try that again. Mucociliary escalator. And the mucociliary escalator here in the terminal bronchial has cilia sweeping up any mucus that gravitates down or is pulled down deep into the terminal bronchioles. It's moving it back up. And that's very important, again, because the alternative is fluid accumulates in these alveolar sacs. We're going to look at that in detail here, but greatly reduces the efficiency of gas exchange. Each terminal bronchiole then in turn gives off a couple of the respiratory bronchioles that then lead to the alveolar sacs. So respiratory bronchioles have these alveoli that are budding from their walls, and this is, at this point, where respiratory bronchioles now expanding out into these alveolar sacs. This is really considered the beginning of the true respiratory division. This is where gas exchange is occurring. Prior to this point, all of this branching is about distributing broadly the gas that's coming into the lungs, and then, of course, collecting up the gases that are from or lost here in the alveoli, lost from the blood, and then enters the alveoli and comes out. So this is the real functional unit, guys. This is what I'm saying. This is where real gas exchange is occurring. And this is, of course, the area that's getting attacked by the SARS-CoV-2 virus and is leading to very inefficient gas exchange. And when that happens, people run the risk of not getting enough oxygen and potentially dying. So we got these alveolar ducts, and they're leading to the sacs. So we're going to look in here a little more deeply. But just a basic question to step back here before we go further. If you think about your respiratory system, and you think about gas exchange, in the lungs, blood is absorbing more oxygen and releasing lots of carbon dioxide. And yet that same blood, when it's in your muscles that are very, very active, for example, or all sorts of organs in your body, including your brain right now, thinking about what I'm talking about, in your brain or any active organs, the blood is giving up the oxygen, lots of it, and taking up a lot of carbon dioxide. That's the reverse of what's happening, the reverse of what's happening in the lungs. So in active organs in our body, gas exchange between oxygen and CO2 is the opposite of what's happening in the lungs. Why? What causes that to happen? And the answer is simple diffusion. It's simply that in the lungs, the blood has more CO2 than the air you inhaled. Hopefully. Okay, that would be really bad if you're inhaling air with high CO2. In turn, what you've breathed in should have higher oxygen than the levels in your bloodstream. Now the blood goes out into an organ. The blood has more oxygen than the organ, and so it loses oxygen to the organ. And the blood at that point in the highly active organ has less CO2 than is being produced and released from whatever active organ, could be the liver, could be a big muscle group, the liver, or a big muscle group. Okay, so this is the exchange of gases that's naturally going on just due to simple diffusion. Here looking at even more detail, and this is really a very important image you really want to take a look at here and study this in great detail. Here we're looking, seeing the pickup box right here is showing you the great detail of the actual respiratory surface. Here, don't be confused, these are simply tubes. It's a little confusing when I first looked at this. Here's a capillary. It's cut in sections, so there's 2 red blood cells inside. And this is the edge of a capillary coming up. Here's a couple more cross sections of capillaries with 2 red blood cells in each. This is the inside, the alveolar sac. This is where the final gases that you have inhaled reach, and in turn, this is where you start exhaling. Okay. And what you see is that the wall of the alveolar sac is composed of a simple squamous alveolar cell right here. And then as they show you in further detail, so this is a pickup right here of that spot, and now this is a pickup of that spot. So we're looking at this in much more detail. Here's the part of the simple squamous cell that's lining the alveolar sac. And then there's a basement membrane we call a basal lamina, because it's not a membrane, so I don't know why they do this. We know better than to do that, but they're still doing some old terminology that is confusing. It's a basal lamina, okay, right here in this book. And then over here, what you're seeing is a capillary endothelial cell. It's labeled right here. And that's also a simple squamous epithelium. So simple squamous epithelium, right here, a basal lamina, and another simple squamous epithelium, and it says they're sharing the basal lamina. So guys, appreciate just how thin that is. That is as thin as it gets in the body. We have a very thin cell, a basal lamina, and another very thin cell. On this side of things, we have what's going to be the fluid inside blood called plasma, and we have red blood cells really turning around and tossing around inside the capillary. Over here, this is the air sac of the alveoli. So that's that deep spot deep in here, as shown in here, and now here. So, what I just described before, this is blood returning. So it's a vein that's led to this, and it's blood returning from the body, returning from very active organs. Those very active organs have produced CO2 and depleted oxygen. Not completely, by the way. Blood at this point still has plenty of oxygen, and CO2 is also abundant. So by simple diffusion, CO2 moves out of the bloodstream into this air space right here, and oxygen moves into the bloodstream. So this is showing the same thing, gas exchange. I don't know that you have this figure in your book. I don't think so. Same relationships we just talked about. Here, just one of those figures where they highlight things. Here they're highlighting these air spaces. And notice the very, very thin walls that we're seeing of the alveolar sacs. Okay. Here they've highlighted a respiratory bronchial, and here a pulmonary blood vessel. Within that alveolus, what we just looked at, we just said that there are an endothelium from capillary, a simple squamous cell from the alveolus. And we're going to take these one at a time. So the alveolar simple squamous cells, these are the really flat ones that are forming the actual walls of the alveolus. About 95% of the surface. So this is it. This is by far the most abundant cell. There's another cell type, and these cell types, which are a little more rounded that you saw in the picture, form only about then the other 5% that are forming the walls of the alveolus. And these have really important functions. These great alveolar cells are repairing things. Okay? So they're repairing the alveolar epithelium when the 95% right up here, the squamous alveolar cells, are damaged. The alveolar cells also do something else that we're going to spend a good amount of time talking about. And so that's the pulmonary surfactant. Now, when you think about these flexible alveolar sacs, they have no internal skeleton or any form of support. The potential's there for these wet sacs to stick together. Imagine you've gone to Walmart and gotten those very, very thin plastic bags to bring your groceries home. and somehow there's wetness inside the bag. Now you've taken all your groceries out, the inside of the bag is wet, your groceries are out, you put the bag down someplace, and when you pick it up, you try to open up the bag. But again, the inside of the bag, we said, got wet. Maybe it was something very cold, and so you just had moisture on the surface. The inside of that plastic bag will naturally stick together and not easily come apart, because fluids like that, the hydrogen bonds of water, are going to hold the sides of the bag together. That's exactly what happens potentially in the alveoli. The alveoli could be sucked sort of closed. You could think about it that way, or adhering is what it is. It could be adhering, the walls could all stick together and not be open. So that requires a different kind of a fluid inside called a surfactant. Now, what a surfactant is, you can see a mixture of phospholipids and proteins that they're coating the alveoli, they're disrupting these hydrogen bonds between the water molecules, and they reduce the surface tension between the inner walls of the alveoli. Okay. This might be a good place to pause and really to write some of this down and to study it. This, of course, is well described in your textbook. So when you exhale out and are removing lots of the gases that are in the alveoli, the alveoli don't collapse and stick together. So here from page 865, a surfactant, which is what we were just talking about, is something that's disrupting these hydrogen bonds and reducing the surface tension. And here in your textbook, they add that soaps and detergents are everyday examples. So in theory, if you had a Walmart bag stuck together, moisture inside, there's nothing else inside the bag, you've taken the groceries out. In theory, if you added some soap to the inside of that bag, and it would need to be a very thorough application of soap, it would reduce the likelihood that the walls of the bag will stick together. Now, I've been talking about these surfactants right here, reducing surface tension. So where in this diagram do we see surfactants? And it's this bluish layer right here. Trying to see if it's labeled. Yes, fluid with surfactant right here is on the inside of the alveolus sac. Now notice that here's in brown, so we're going to look closely over here. Here in brownish color is that inner squamous cell, and the surfactant's on the inner surface of that cell. So this is a fluid, this is the surfactant is a coating, a fluid coating. Think about it that way. And that's so very important. So let's talk about this. It turns out that this is a relatively new understanding in medicine, and it's been about 60 years since modern medicine has really taken a hard look at this problem. And the problem is, if a baby is born too early in a pregnancy, so it's premature baby, the surfactant may not be sufficient for the newborn baby to be able to breathe on its own. Okay, let me say that clearly. Surfactant production comes along later in a pregnancy, and if you have a premature baby, that premature baby may not have sufficient surfactant to keep the alveoli open and allow it to survive. And here, newspaper article, and this is very significant. This is not just me off on a tangent, because I'm going to lead to a major thing in medicine here. So I'm going to lead to an important point here. The baby, as you can see, it says, lived for 39 hours prematurely. Baby, although it was a healthy weight, did not have enough surfactant, and we called that, at the time, hyaline membrane disease. That's just an odd name. It doesn't really work. So here, they're saying a half century ago, but now it's 59 years ago, is when all of this tragedy happened. So you can see August 7th, 1963 is when this happened. In November 22nd of 1963, President Kennedy is assassinated. So just 3 months later, poor Jackie Kennedy has not only lost a baby, but lost her husband. So, the death of the presidential baby, now 59 years ago, was a critical event. And here they're saying, according to historians, it was the stimulus, the spark that got some things going in medicine for premature babies, just like the launch of the Sputnik satellite by the Russians promoted our space race. Well, here's another side note that I'm adding. That same year, a Canadian doctor had already started to address this problem. And to be clear, this means then that some of the best medicine available to the President of the United States was not being applied, and that a better solution, something that would have saved the baby, was known in Canada. But, guys, medical information needs to spread. Practices need to spread. New ways of doing things need to be adopted. So, today about 95% of all infants diagnosed with this problem survive. Okay? Today, there's over a 95% chance of addressing this. It's called respiratory distress syndrome. That's what we're talking about, a premature baby with insufficient surfactant. Respiratory distress syndrome, RDS, and as it says here, more than 16,000 premature babies in the U.S. The March of Dimes is helping to address this as a nonprofit. They lack the protein surfactant, but we now know how we can address that. And here's my point. There's a whole branch of medicine that has emerged in the last 60 years that focuses on the unique physiological needs of premature babies. And so it's neonatology, and it has given rise in most modern big hospitals to a neonatal intensive care unit that's briefly called a NICU. So some of you may know about NICUs, and you may know about the intensive care that's needed for some of these premature babies, and this is a big part of that story. My daughter got her doctorate in occupational therapy at Washington University, the #1 program in the nation. And while she was there, she was working with a professor whose focus, her research focus, was on occupational therapy needs for premature babies. So my daughter, right away, she joins the program, and she's working in a NICU down in St. Louis. And I was telling her, just a couple of years ago, after she's graduated, I said, did you realize that this whole President Kennedy disaster, the loss of a newborn baby, that was actually pivotal in the establishment of NICUs and neonatology? And she said, oh yeah, Dad, we went all through that was a big part of our program. They were very clear that NICUs essentially came about because of a tragedy with a presidential child. Yeah. It's a shame, isn't it, that we have to have disasters to make this kind of progress? Well, the third kind of cell that you find in an alveolus are called alveolar macrophages. Sometimes called dust cells because, as you can guess, what they're going to be doing is cleaning up things that are inhaled. Now, on page 856, Saladin says they are the most numerous of all cells in the lungs. I looked because I thought right away, really? More than red blood cells? And so I don't know the answer to this. It's my own question, and I'm sharing it with you. I wonder if they mean the most numerous of all lung cells, not talking about red blood cells. Nonetheless, we got a lot of them. Why? Because they're wandering all around and they're helping to remove anything that we've really inhaled. So if you're in a real dusty environment, you could guess that. They're going to probably be involved in removing damaged cells, infected cells. And right here it says 100 million dust cells die each day as they're destroying things, phagocytizing things that we've inhaled, and then they're moved up the respiratory tract by that mucociliary escalator, and then of course they're swallowed into our digestive tract. Now, before I mentioned to you that that mucociliary escalator in some of these terminal bronchioles is moving up fluids that have somehow either by gravity moved down deep into the lungs or perhaps just by inhalation are moving deeper into the lungs, and that we do not want fluid to accumulate in the alveoli. Why? Because gases diffuse too slowly through a liquid. Alveoli are largely kept dry by absorbing fluids that are there into the capillaries. Okay, and there's also a really good lymphatic system that's helping to remove some of these fluids. And there's really low capillary blood pressure, and fluid could leave a blood capillary system. So they're all blood capillary systems. It could leave a capillary system if the pressure is high enough. So it sort of squeezes the fluid out through the little thin walls. Here we've got a low pressure system that might actually be draining away some extra fluids. All right, so that's it. We're talking about the alveolus and its functional significance. There is a lot to be studied, and I strongly urge you to spend some time really looking this over in the textbook, learning more cool things about how the lungs work. And that is really the essential background, the essential foundation for you to understand what's going on with COVID. Okay, so some of you might be going on to nursing, and COVID, I hope, will be subsiding. You know, some of the hope, just to talk about this briefly, for COVID, it's not just vaccines. We think the vaccines will be getting better and perhaps more broad and able then to vaccines able to be effective against new variants that arise. But the other hope is that the drugs that we have to help people fight COVID disease are coming along. Pfizer's already got a pill that's amazingly effective. It just takes a really long time for them to make the pill. And so we do not have enough of the pills. But with time, Pfizer and other companies will probably make more and more drugs where if you have a COVID infection a couple days in, but don't wait too long, you can start these drugs that will really reduce the effects. So who knows what it'll be coming along. Maybe it will be still dealing with this. And of course, there's all sorts of lung disease that you might be addressing. But many of you are interested in going into medicine and are likely to enter a field still fighting COVID or COVID-related problems. And of course, flu viruses have been a persistent annual problem. And as people get older, they have trouble fighting it. So, boy, understanding this, guys, I'm just telling you, it's a really worthwhile investment. It also helps you understand asthma. Also helps you understand people that are inhaling crazy stuff like smoke. Deliberately inhaling smoke. That's smoking. And that's smoking for unfiltered, of course, joints. So pot, marijuana, those are unfiltered cigarettes that are really, really bad for your lungs as a way to get in the effects. If you wanted that recreational effect or medicinal effect, I would suggest you use edibles. Don't be breathing pot into your lungs. If you want to do pot and it's legal for you to do so, I'd strongly recommend that you use the edibles. Okay. But even vaping. So what about vaping? You could ask Dr. Slisko, does that seem okay? Well, we know of all sorts of problems that are springing about from vaping, and we're learning more and more about the impact on the lungs. I'm not going to go through that now, but I'll tell you that I know of a death of a student of the typical Blackburn College age, so in late teens, early 20s, and the person, as his friend said, he pretty much vaped nonstop, and he died. And we don't know what actually contributed to the problem, but we know that a lot of vaping certainly didn't help this person. Okay, we've talked about these cavities. I talked about the pleural cavity. So we have visceral pleura, and that's the covering of the lungs. We have parietal pleura, that's the lining of the cavity, and we have, in theory, a pleural cavity. And I say that because, yes, it does exist, but more in a diseased or trauma situation. We talked about that stickiness between two thin layers when there's a fluid involved. And normally, the parietal pleura is stuck to the visceral pleura. And that means, so you got to really follow this, when your chest expands, it expands the lungs. And we're going to look at the chest expansion here in just a second. So the visceral pleura covers the lungs, parietal, as you can see, adheres to the mediastinum. So I've been talking about that, the midline of the body, when you're opening up the cats for the digestive system dissection. And the pleural cavity is this potential space. Normally, there's no room. There's just a fluid called pleural fluid. Big surprise. What is it that's going on with the pleurae and the pleural fluid? Well, for one thing, as you breathe in and out, it reduces friction because there would be some friction on the lungs. And it helps to pass along the pressure gradient that helps then to lower the atmospheric pressure inside your lungs. So as you expand the chest cavity, it lowers the atmospheric pressure inside the lungs and it assists in inflation. It also provides a compartmentalization that we talked about before when I talked about buildings and fire doors. So the reduction in the spread of damage or disease. Okay, so bleeding or any kind of damage from an infection. Hopefully it'll move more slowly throughout the organ. So preventing, as you can see, the spread of infection. Here's that parietal and visceral pleura. They're showing you a little bit. It's kind of an incomplete view. So these aren't the best pictures that help me. I'm not quite sure what's going on here, why this is patchy. Maybe I'm just missing something. Here the lungs have been cut, and so the surfaces are a little more revealed. As we move on, talking about breathing. Why do we breathe? Why can't you just take in a big breath and that's good enough for an hour or 2 hours? There are organisms that do that. There are organisms that are ectotherms that don't require a lot of oxygen and who are not very active and are probably in a colder environment that can take a breath, go into the water, and not be breathing for a long time. So why do we breathe? And simply enough, as we breathe in air, the oxygen, the higher oxygen that's in the air we breathe, diffuses rather quickly into the bloodstream. And so the difference in the high level of oxygen in the air we breathe and the level of oxygen in the blood we have, that difference drives the diffusion. But as that difference decreases, diffusion becomes less efficient. And so we might just benefit by taking a new breath of fresh air and then increasing that differential in the levels of oxygen between the air you breathe and your bloodstream. Same exact things happening then in the other direction. CO2 levels are high in the blood, relatively low in a fresh breath that you've taken into your lungs. CO2 diffuses out into that breath that you've taken in, and then the differential decreases, the diffusion out of the bloodstream of CO2 is decreasing, and you take another breath of air and increase that difference between CO2 and oxygen levels. Okay? So that's why you're breathing. You're making that change. But somebody said something recently, I don't know, recently for me is the last 10 years, and made me pass along something else that just really made me chuckle. There's sometimes an impression that when we breathe out, we have depleted all the oxygen in the air that we had breathed in. That is not true. And how do you know that? Well, mouth-to-mouth resuscitation, or someone needs you to breathe air into their lungs, Mouth-to-mouth resuscitation would not work if the air you breathe out lacks oxygen. The air you breathe out has less oxygen, if you're alive, than the air you breathe in. But it doesn't have it has some when you breathe out. It still has good oxygen when you breathe out. Okay? And likewise, if you're not breathing, is there still oxygen in your blood supply? Yes, yes. And that's why the advice changed again in the last 10 years, probably in the last 5 years, where in CPR, which is cardiopulmonary resuscitation, someone's heart is not working and they're not breathing. And so in CPR, you're doing both rhythmic compressions, very fast, like 100 compressions a minute, to compress the heart and to move along blood through the person's body. And in theory, you're giving breaths. But if it's just one person, that's really hard to do the compressions and the breaths. And you're probably going to have to stop compressions to give breaths. So the advice changed. If you're by yourself giving CPR, don't do the breaths, just do the compressions. And hopefully you can be calling for help. And that's because moving the blood through the body is actually more important than giving the breaths, because the blood is still containing a lot of oxygen. Okay? We just want to move it around so that when the blood is getting depleted in a particularly active organ like the brain, we can move more blood that's got a fresher supply of oxygen in. So, this simple question of why do we breathe turns out to have lots of interesting sidelights. So pulmonary ventilation is breathing, okay? And what we're doing in breathing is moving a respiratory medium past a respiratory surface. That's not up here, but that's a broad definition from comparative vertebrate anatomy. So whether or not you're looking at gills or lungs or the skin, if we're doing some kind of ventilation, we're moving a respiratory medium, which might be water or might be air, past a respiratory surface, which in our case is lungs, but it could be gills. So in axolotls, they breathe, and another thing they do is they twitch their gills. And so if they're in very low oxygen water, they'll twitch their gills, that is, move them back and forth. And they do this sometimes about every 10 to 15 seconds. And they do that to get a fresh supply of water there that's a little higher in oxygen content and lower in CO2. In our respiratory cycles, we have two different types of breathing. We call it quiet respiration, which, as you can see, is pretty automatic. And then, of course, we can choose to take a bigger, deeper breath. And that also may be automatically triggered. So my wife and I will brag about this all the time, but I think it's important that you know that old farts like me are still thinking that it's really important to exercise. And so we take lots of walks. Already taken 14 here in January, so that's every other day, even though it's been really cold outside. And we walk 2.3 miles on a road that goes up and down a lot. So there's a couple long, steep hills, because I live in Forest Hills subdivision on Ridge Drive. So you got the idea that it's not flat around here. And when we're taking these walks, and we're in pretty darn good shape, we still are going up these hills, and I watch my breathing, and I think, well, I'm doing pretty well. And then at some point, I just find myself taking an extra deep breath, usually when I'm right near the top of the hill. So you might take a bigger, deeper breath when you're exercising, because you really aren't keeping up, okay? And of course, the weird part about talking about breathing is that as soon as you do, you become aware of when you're breathing. And then for me, it's not panic, but there's a little part of thinking, okay, so at what point do I not be thinking about my breathing and I do something else and I trust that my automatic system, my autonomic nervous system, will take over. And I'm going to trust that that's going to happen now. So why is there a movement of air? It's because there's pressure differences. And that has to do with expanding the thoracic cavity or compressing the thoracic cavity. And there are respiratory muscles that are involved in this, and they include muscles of our chest and also the diaphragm. Here's just a superficial look at a cadaver dissection. Boy, that is a very nice dissection. You just don't know how much work that took to produce this dissection. So here we see the abs. The six-pack abs, as you can see, is 1, 2, 3, 4 is really an 8-pack ab. Here, the places where the muscle sections are connecting are called inscriptions. And you can see that there are 3 sets of inscriptions here. The rectus abdominis is involved in breathing as well as almost all the muscles you see. Now in this particular figure, 2213, I do want you to study and I do want you to appreciate what all these muscles are doing. But right now, that's not what we're going to do. We're going to look at that in just a couple minutes. So right now, just look and notice that there are a lot of these muscles, both the diaphragm down here and muscles that you've identified already. So pectoralis major, pectoralis minor, this is minor. External intercostals and internal intercostals. Sternocleidomastoid up here, and maybe we did the scalenes on the models. Now that would have all been in Human Anat Phys 1, BI251. So now just talking more specifically about these. Diaphragm, of course, is the primary mover, and what I've talked about before is that it's dome-shaped when it's relaxed, and so it contracts and flattens. And I would hope you appreciate that an arc is a greater distance than a straight line. And that's because when a muscle contracts, it's over a shorter distance. So a dome contracts into a pretty straight line. Okay. Then it relaxes and expands up back into the dome. So bulging upward again, as it says on the screen. And the diaphragm is responsible for most of the airflow. Now, there's individuals doing different kinds of things. And here is the highlighted diagram that you don't have in your book that's showing you this dome shape of the diaphragm. And here you can see it closely parallels the shape of the liver, and then over here would be the stomach. So this is a bit more firm over here in the stomach on this side. Here in a view, we're looking between the ribs with muscles removed. So the intercostals are removed so that we can see here the diaphragm. Another view of the diaphragm. Of course, lobes of the lung, the heart. Here the aorta coming up and branches coming off. These are common carotids, likely, and parts headed to the arms and legs. So external, internal intercostals. You can read aloud what's on the screen. These are descriptions. This parallels what was in that figure. And you can see how these skeletal muscles are contributing then to breathing. The scalenes are up here by our clavicles, and they ask you to actually feel them. So you can put your hand in about this posture, and gently, after you're doing this, take a big deep breath, and you'll feel those muscles expanding. Here's the scalenes in a different view that you're feeling when you're breathing in on these cadaver dissections. Just really great images for you to learn about the functional morphology of a human being. Normal quiet respiration, you're not thinking about it much. It's, as you can read, it's based a bit on the elasticity of all the system. Muscles relax, air flows out. You can voluntarily force air out and using an awful lot of the muscles we just looked at, rectus abdominis, these intercostals, and even lumbar and abdominal musculature, even pelvic. Greatly, you do those muscles right in here to greatly force air out. Well, that might be like inflating a balloon, okay? I'm not sure when else you're forcing air out. Well, coughing, I guess, sneezing, choking. Those are things where you're going to want a greater expulsion of air. And these muscles are really important for those people in choir and other musical instruments where you blow. So I played the trombone for a long time, and that you're trying to blow a lot of air out. So I guess that would be another reason you're doing this. And I learned to use this musculature to generate a great force. The Valsalva maneuver, we talked about a little bit before, in that we're trying to expel feces. This is where you take a big deep breath, and then you don't let the air out, but you still generate those abdominal muscular pressures. So you're using the musculature to exhale, but you're closing the glottis. And so when would we do this? Well, we just talked about it in chapter, I think, 25 on defecation. But here you can see other circumstances like childbirth or vomiting when you might be using those muscles. And so here's this figure again, just for you to review of all this kind of musculature that is involved in breathing. And that brings us to the end. And so this is a good stopping point for Lecture 9.